Welcome back, everybody. I'm very pleased to introduce Mariya Soskova, who will speak on one-point extension of antichains in the local structure of the enumeration degrees.
Thanks, Paul. Thanks, everybody, for giving me this opportunity to talk. I'll be talking about some joint work in progress. So some of the theorems will be starred with John Lego, Selwyn, Yang Meng, and Stefan Lem. So this goes back to a classical question in degree theory that arises almost as soon as you define the structure. Okay, so suppose you're thinking about a degree structure, and for the purposes of this talk, we're going to be looking at the Turing degrees, the enumeration degrees, the delta 2 Turing degrees, the CE Turing degrees, or the sigma 2 enumeration degrees, which is kind of the local structure, the initial interval of the enumeration degrees below its version of the jump. And then once you have such a structure, you may think about, well, how complicated is the theory of that structure? Is it decidable, right? And almost always, well, not almost always, the answer is no, not decidable. And in fact, each of these structures has maximal complexity. So in the case for the global structures, the Turing degrees and the enumeration degrees, it's as complicated as second order arithmetic. And for the local structures, the other three, it's as complicated as first order arithmetic. And you can throw in here, you can consider other structures. You can consider the m degrees or the n degrees below zero jump. You can consider in the other direction, the arithmetical or hyperarithmetical degrees, and they all fit in the same answering scheme in terms of these questions. So then you say, okay, well, let's change the setup a little. Let's focus on very simple questions. Like let's restrict the quantifier complexity of our question. What about just existential questions, existential statements? If you think of the existential theory, is that decidable? Okay, so what does an existential sentence say in a degree structure? So remember, the language is just the language of the ordering. So an existential sentence says that there are finitely many degrees. They relate in some way to each other. So in order to say, yes, this existential sentence is true, all you need to do is embed a partial order in the degree structure. And in all of these cases, all partial orders, finite partial orders, can be embedded into the degree structure. So each structure has a decidable existential. So we have this gap, right? At the existential level, the theories are all decidable. At the full level, full quantifier complexity, the theories are all maximally undecidable. So then the question is, how many quantifiers does it take to break down decidability? And surprisingly, the answer always seems to be following the same scheme. Whenever there is an answer, it breaks between two quantifiers and three quantifiers. So 3 quantifiers is undecidable, 2 quantifiers is decidable. And since I'm looking at a lot of structures and a lot of results here, I've summarized them in this table. I won't go through all of it, but you can see references. So the first column in this table gives you references for who proved that the corresponding global full theory is maximally complex. The second column, and in each case we have an answer here, the 3 quantifier theory is undecidable. That's the result with the corresponding references. And then the last column, we have decidability for the 2 quantifier theory. And those results that are known are due to Shor and Lerman. And they're only known for the Turing degrees and the local structure of the Turing degrees. For the C Turing degrees, for the enumeration degrees, and for the local structure of the enumeration degrees, we don't know if the 2 quantifier theory is decidable or not. And it's an interesting question. There's a reason for this big gap. So there's a reason why these remain open. There's a difference between the structures for which the problem is solved and for which it's not. and that is density, right? And then the Turing degrees and the local Turing degrees, there are minimal degrees. And minimal degrees play a role when in the deciding algorithm for the quantifier theory. They're very useful. The enumeration degrees are downwards dense. This was proved by Goodrich in 1971. The CE degrees and the sigma 2 enumeration degrees are actually dense. So results by Sachs and Cooper. So that is a fundamental difference between these structures that makes the question more complicated. And I will say more about how it's more complicated. Okay, so focusing now on the two quantifier theory, how do we understand whether a two quantifier sentence is true in a degree structure? Well, we can translate this in a structural way into the following problem. So we're given a finite partial order P, and we're given finitely many possible extensions of P, Q1 through Qn. And the question now that we need to decide, just based on P and the P and the Qs, is whether every embedding of P into the degree structure extends to an embedding of one of the possibilities, one of the Qi. Okay. So that is the problem that the big problem that we would like to someday answer for the structures for which it's open. The case when n equals 1 is known as the extension of embeddings problem. So there, I just have one possible extension, Q, and I'm asking, does every embedding of P extend to an embedding of P? And for the Turing degrees, whoops, I've missed here the zero jump. The Turing degrees below zero jump. The case where n equals 1 is decidable, and that was proved by Lemon and Shor, but it's more than that. Okay, now let's stop moving. There we go. It's more than that. The case where n is bigger than 1 can actually be reduced to the case when n equals 1, because it turns out that every embedding of a partial order P extends to an embedding of one of the possibilities Q1 through Qn, if and only if one of the choices we have, one of the Qi's, has the property that the corresponding extension of embeddings problem for P and that Qi has a positive. So if the answer is yes, there's always one Q that works. Okay. So, right, and the way that you prove this is you have a maximally complicated embedding, an embedding that's maximally hard to extend. And that embedding embedding is embedding P as an initial segment of the corresponding degree structure, right? Initial segments use very much the existence of minimal degree, right? So the least element of P goes to 0, the atoms of P go to minimal degrees, then the next level goes into minimal covers over those minimal degrees, and so on. So you can do that in the Turing degrees and delta 2 Turing degrees. You can't do that in the other structures because they're downwards dense. So the problem is different. The extension of embeddings problem, so the one where n equals 1, is actually decidable for each of those structures, but that turns out to be not enough. Okay, and we'll see an example of how that's not enough. Okay, so we have this more complicated problem. And in order to kind of get started on it, we're going to focus on a subproblem, which, and we're also today going to talk only about the local structure of the enumeration degrees, but you can investigate the same sort of situation in the other two structures where this problem is open. And as far as I know, we don't have solutions, at least not yet complete solutions to any of these, even for the subproblem. To be fair, I haven't really investigated the C Turing degrees that much, but Stefan maybe knows more about it. We can ask him. Okay, so here's the subproblem that we're going to look at. So we're given a finite antichain P. So we're fixing what type of partial order P is. It's an antichain. And we're only looking at 1-point extensions. So we're only adding 1 point in each possible case. And we're also going to restrict things so that every new point is below some element in P. And then we're going to ask, does every embedding of P into the sigma 2 enumeration degrees extend to an embedding of one of the QI? So we're still giving different possible choices for the Qs. But we're going to exclude 0 and 0 jump. Well, 0 jump doesn't play a role in this case because we're always putting elements below some element of an antichain, but we're going to exclude 0 as a possible extension point. So this just kind of rules out some trivial answers. Okay, so why this subproblem? Well, come on. No. All right, so first of all, our first step is, well, we would like to have a simple partial order P that we're thinking about. And the simplest possible partial orders are chains or anti-chains, right? The problem with P is a finite chain and QIs are 1-point extension. This has an easy solution. It's solved using a variation of Cooper's density construction. And the solution appears already in the extension of embeddings. And the extension of embedding solution by Lemp, Sorby, and Slayman. Similarly, if P is an anti-chain and QI adds a point to the side and comparable to any elements of P, the answer is always yes. In both of these cases, the answer is always yes. And the similar sort of argument works in this. So those are easy cases that we can solve. Then we can think about the dual problem. So why are we placing a new point below and not above? The dual problem of placing an additional point above, again, in this case, excluding 0 jump, is easily seen to be decidable as well. And the methods that are used here are density and the fact that every pair has a least upper bound, and we can make that bound equal to 0 jump. Now, as we know in degree structures, not every pair has a greatest lower bound. So that's why putting a point below some element of the anti-chain is hard. So that's the first point where we encounter a complexity that is actually hard to figure out. So motivation for why this exactly problem we're going to look at. And okay, so now that we're thinking about this problem, here it is phrased again. We're going to represent an instance of this problem as an anti-chain of size n. Okay, so an instance of the problem is an anti-chain of size n. We're going to represent by the natural numbers 0 through n minus 1. Extensions QI are going to be represented by subsets of the numbers 0 through n minus 1, namely, so every QI adds a point below certain elements. So it's represented by some non-empty subset of the anti-chain, namely the indices, the points that bound this new element. So ultimately, an instance of our problem is going to be a set like this. So it's a set of finite sets, each of them a non-empty subset of n. And a solution to an instance is yes or no, right? Yes meaning every embedding of the anti-chain extends to one of these. No meaning there is an embedding of the anti-chain that does not extend to any. Okay, so now we don't necessarily have to, in every case, solve all instances. There are some connections between instances that I like to highlight here. So suppose you have two instances, S1 and S2, and S1 is a subset of S2. So S2 gives you more possible choices. All the choices that S1 gives you are there, and S2 adds some more. Well then, if S1 has a positive answer, like if I can always extend given my small number of choices, then I can always extend given my larger number of choices. So if S1 is a subset of S2 and S1 has a positive answer, then so does S2. And similarly, if there's an embedding that doesn't even extend to the larger number of choices, S2, then the same embedding will serve as an example of one that gives the no answer to the first instance. So that's a simple relationship. And then there's one more relationship. If you can obtain S2, and here S1 and S, for the third one, I guess I should have typeset it better, but for the third choice, S1 and S2 don't need to be related. One doesn't need to be a subset of the other, but instead, if S2 can be obtained from S1 by a permutation of the numbers from 0 to n minus 1, then S1 and S2 have the same app. Just because we don't put ordering. Our antichains are not ordered. So, okay, so these are the relationships. Now to get us started, let's look at the case where we just have two elements, and this will allow me to introduce the main players in this sort of problem. Okay, so here are all the instances when the partial order is just a two element partial order, 0 and 1. Some of them are blue. The ones that are blue are the ones that satisfy this this permutation property, right? 1, 0, 1 is a permutation of 0, 0, 1, and 1, just 1 by itself is a permutation of 0. So those are kind of, will fall out. We don't have to consider them separately. And we're looking for a dividing line between the yes and no answers, because if this, for example, has answer yes, then the point above it will have answer yes. If this has answer no, then the points below it will have answer no. So that's why dividing line in order. Okay, so so fix an embedding of P to incomparable sigma 2 enumeration degrees, A0 and A1. And let's first consider the instance 0, 0, 1. Okay, so we have density here. Downwards density is enough. So by downwards density, there is some non-zero degree X such that X is bounded by A0. Now we're given all possible choices of how this X will relate to A1. Either it's just below 0, in which case we can always extend to 0, or it's below both 0 and 1, in which case we can always extend to 0, 1. So in this case, the answer is yes. Okay. Now we can consider 0, 1 here as a second step. And this one we can block. We can block it by making our embedding of P such that A0 and A1 form a minimal pair. So if A0 and A1 form a minimal pair, and there are minimal pairs of enumeration degrees, then there's nothing that's non-zero below both A0 and A1. So the answer to this instance will be no. Okay, any questions here? Because it's it's the most basic kind of setup here. That if people want me to go, if people want to have questions about how the instances work, I don't want to lose you just yet. Yes.
I didn't see if these answers imply all of the answers or not.
Not yet. No, we haven't done. I'll show you what they imply. So this is what we know. So we're given a yes answer to this one. This automatically colors the top degree yes as well. And the one that was obtained by permutation. So these are the greens we get. This is the red one. Doesn't tell us much more. So we still have two things that we need to figure out. We need to consider 0, 1, and 0 in order to have a full. Thanks. Okay, good. So now let's consider 0. Okay, so suppose that we have an embedding of P such that every degree that's strictly below A0 is also below A1. Now, this is something that can be done in the sigma 2 enumeration degrees. Ahmad showed that there are such sigma 2 degrees. So we do have an embedding of this kind. And so the answer to this particular instance is no. But on the other hand, Ahmad also showed that you can do that symmetrically. So if we consider now 0, 1, our natural way to block it is to do the construction we did in the first case symmetrically. Everything below 0 is below 1, everything below 1 is below 0, but you can't. So Ahmad showed that if every degree below x strictly below A0 is also below A1, then there must be some degree y below A1 that's not below A0. And so the answer for 0, 1 is yes. Okay, so now we have a full picture. The dividing lines turns out to be straight. So we have no answers at the bottom, green answers at the top. And the main players, what did we use? We used density, minimal pairs, and Ahmad. So those are our main players here. And this already illustrates that there is a difference between the extension of embeddings problem and the more general problem that would need to be considered for the full 2 quantifier theory, because notice that each of 0 and 1 individually can be blocked. But if you give both options, 0 and 1, then the answer becomes yes. So we don't have that nice property that simplified the situation in the case for the Turing degree. Okay, so case n equals 2 is solved. And before I move on to more complicated cases, let me just tell you more about the main players. Okay, so this is the definition of Ahmad pairs again. So degrees A and B are an Ahmad pair. We're going to write this as A of AB. If A is not below B, and for every X that is strictly below A, we have that X is also strictly below B. So maybe if you would like this drawn somehow, we have A here. These are the degrees strictly below A, and B is somewhere, it's actually incomparable to A, but the degrees below B include everything strictly below A, but not A itself. So it follows that by definition, A is not below B. It follows that B is not below A as well, because we have density. If B were strictly below A, there would be something between A and B that B can't be above. So they are incomparable degrees, these Ahmad. There's another interesting property that they have. If A and B are an Ahmad pair, A is non-splittable. You can't write A as the join of 2 degrees X and Y strictly below. So this doesn't happen, right? Because, well, if X and Y are strictly below A, they'll both be below B, and then their join will be below B, but their join is not below. So they're non-splittable. And non-splittable degrees are actually easier to build than Ahmad pairs. In fact, Kent and Sorby showed that there's one below every non-zero sigma 2 enumeration. So every non-zero sigma 2 enumeration degree bounds a non-splittable degree. And so Ahmad's construction went as follows. So start with a non-splittable degree. She actually constructed one. And she constructed hers low. Start with a low non-splittable degree. And then she had these 2 really cool lemmas that made the whole thing work. So first, if A has low non-splittable degree, then you can list in a uniformly sigma 2 way a sequence of sets BI such that BI generate the ideal of sets that are strictly below it, which I think is a really powerful thing, right? To be able to generate that is, I mean, if it's a non-principal ideal, that, yes, Ori? Yeah. Oh. Yes, sorry, I guess I didn't phrase that well. BI is below A, all strictly below A, such that essentially the ideal of things below A is you close the BIs down. So you can list that in a uniformly sigma 2 way. And then once you have that, so if A is sigma 2 set, and you can list, you have some sigma 2 sequence of sets such that A is not below BI. So I guess maybe she didn't even need the BIs to be below, not sure. But then you can build a set B that bounds all the BIs, but does not bound A. So the second step here is kind of difficult. It's a difficult construction, technically challenging. But the third step is not that difficult. It's one that follows ideas, again, that come from density, from the density construction. Okay, so she has this nice modular way of building Ahmad pairs. And of course, when we're thinking about these complicated constructions, sometimes modular proofs are not enough. You need an actual direct construction, and there is one. Lemp and Sorby gave such a direct construction of Ahmad pairs on a tree. This was in a proof in which they showed that every finite lattice can be embedded in the sigma enumeration. Okay, so we have a modular proof and a direct proof. So we have options here. And for symmetric Ahmad pairs, the situation is similar. Sorry, I'm having delays here when I'm switching between slides. So that's why I pause this occasionally. Okay, so there are no incomparable sigma 2 degrees A and B such that A is an Ahmad pair with B and B is an Ahmad pair with A. So that's the no symmetric Ahmad pair statement. I've attributed it here to Ahmad and Lachlan because, well, Ahmad wrote a thesis in which this result features. Ahmad was Lachlan's student, but then the paper from which I got this particular proof is by Ahmad and Lachlan. So I'm not entirely sure how the result could be attributed. I'll just give the more general attribution. Okay, so here's how this proof went. It's again very modular and I think very cool. So she used the ideas that came from Goodrich. So Goodrich, remember, he was the one who showed downwards density in the sigma 2 enumeration. So he built an enumeration, a special enumeration operator, theta, that had the following properties. So first of all, every column of theta is finite. And furthermore, zero jump can compute uniformly and then the bound on each column, so that everything strictly below this bound Bn is in theta, everything strictly above Bn is not in the column. I'm using these square brackets and to represent the nth column. And so we only the Bn's remain undetermined for now. And and this is that they kind of code X. So for every n, we have n is in X if and only if the Bn is in the nth column. So that is those three properties were there. And then also theta was constructed so that if it turns out that theta of X is equivalent to X, then X is CE. So this is a little harder to explain how exactly he did that. It involved the construction, but those are the properties of theta. So in particular, so the third thing says that if you start with a non-CE X, then theta of X is strictly smaller. And if theta of X is CE, well then, because X is coded in this way, it will turn out that zero jump can compute X and decode, can figure out where these Bn's are, and it computes the C set, so it can recover X. And then for X delta 2, it was already known that delta 2 sets are downward stenciled. That used a separate proof. But for non-delta 2X, this gives the downward density already. Okay, so that was Goodrich's proof. And then Ahmad took that and said, okay, so let's apply this special Goodrich operator theta to the set which codes in its columns all the sets enumeration reducible to A. So this is kind of like an analog of the halting set. We actually call it Ka for the enumeration degrees. But unlike in the Turing degrees, this is equivalent to A because we only have positive information in the enumeration. Okay, so theta of, we apply theta to this set, the uniform join of all sets reducible to A. Here we fix some computable listing of all enumeration operators. Okay, so if that happens to be bounded by a set B, then we can approximate each of the sets gamma E of A in a nice way relative to B. With an approximation that behaves nicely with respect to some fixed approximation to B. And then using that, having these nice approximations, you can execute Cooper's construction, the one that showed density in the sigma 2 enumeration degrees, to build something that's strictly below B, I of B strictly below B, which is not above A. Right, in Cooper's density construction, we get these nice approximations to the sets gamma E of A just because A is reducible to B. And then we build this set psi of B strictly below A and join it up with A, and that gives us the intermediate degree between A and B. But it turns out that even if A is not below B, only as long as this set theta of A join gamma of A is bounded below B, that's enough to carry out the construction. So I think this is a really nice proof. It really makes sense to me. It takes float things, puts them together. It's not a messy construction. But of course, you can do a messy construction here as well to give a direct proof of Noaa here. And we did this. So this is one of our first results. This doesn't have a star in it. This construction works for sure. So this is a direct construction that proves Noaa here. So fix sigma 2 sets A not reducible to B. We can build an enumeration operator. First, we build an enumeration operator phi 1 so that the set, when we apply phi 1 to B, the set we get satisfies the following requirements. So x1 is not below A, so x1 is not equal to gamma E of A for any E. And x1 is strictly below B. So B is not reducible to x1 is what the second kind of requirement is. Okay, so this would do it, right? This would show that there's something strictly below B that's not below A. Of course, these strategies are going to fail if it turns out that B forms an Ahmad pair with A. And so if one of these strategies fails, then we can build an enumeration operator phi 0 that applied to A produces another set x0 that then we can show is strictly below A, but not below. So we have this non-uniformity built in here. So we try to attack one side, and if it fails, we win on the other side. And we have, for every possible strategy RE, we'll have infinitely many kind of sub-requirements that are trying the other side. And if the other one, okay, so just a little note on how we build, a general idea for satisfying this strategy REI. So the idea here is to code the set A into x0. So we code A into x0, but in a special way. So we're building a set, we're building an enumeration operator psi so that A, so we're trying to threaten that A equals psi of B. Of course, we're given that A is not enumeration reducible to B, so that can't happen. That will have to fail. But we're threatening to build it. And the way we're threatening to build it is by coding A and X1, coding A and X0. But for every element A that we want to eventually enumerate in psi of B, the one that currently seems to be an A, and we want to enumerate in this set psi of B, we have two types of markers, one targeted for X0 and one targeted for X1. And first we put X0, XA into X0 with an axiom that includes the valid axioms for each of the markers for older elements and B that come from this operator gamma E of A, right? So the MBs are targeted for X1. We already assumed that they're there. So we can assume that this strategy fails. So we have equality here. So we can wait for axioms to appear here. We'll take them and use them to put XA into X1. And then we'll wait for this XA to appear in this operator, and we'll use a corresponding axiom that's now gives subsets of B to give axioms for both MA and A and psi. It's complicated. As I was writing this talk, it felt like, oh, I'm going to explain this. It's going to make sense to everybody. But I realized that it's a little technical. The point here is that we have markers in X0, markers in X1, and we kind of intertwine their axioms in such a way that ultimately the fact that there is no such psi, this psi that we're building is wrong, it will end up producing either an inequality in this first set or an inequality in this second. So that's kind of the main idea here. And it gets more complicated once you consider interactions between strategies, but it ends up working. Now, why would you need a direct construction, you would ask? And that was my question as well while we're working on it. I felt very little motivation to work out this complicated, messy priority argument. But my co-authors insisted that we should persevere, and for good reason. So it turned out that this was very useful. Why, you might ask? Well, okay. So there was a problem that appears as soon as you start thinking about our subproblem for 3 or more degrees. And namely, it is, okay, we know that we have Amat pairs, but do you have Amat triples? Can you take these Amat pairs and connect them together to make interesting embeddings of antichains that block things? So in particular, are there sigma 2 degrees A, B, and C such that A is an Amat pair with B, and then B is an Amat pair with C? And then you can carry this on. C is an Amat pair with D, and D is an Amat pair with E, and so on. So we know that, we know from the no symmetric Amat pair that C and A can be the same, but are there such triples? And this problem actually, unfortunately, people worked on it for many, many years in various configurations, all including Stefan. And for some time, they were working under the assumption that the answer to this question is yes. And that is what stalled things for a while, because actually it turned out that the answer is no. Before I tell you what the theorem is, though, I wanted to save some time here and introduce another notion that plays into plays in when we consider larger instances. Okay, so it's a small generalization of the idea of an Amat pair. So so far we had Amat pairs for degree A and degree B. We're gonna switch the degree B by a finite set. So if A is a degree and F is a finite set of degrees, such that A is not bounded by any element in that finite set, we'll say that A forms a generalized Amat pair with that finite set if and only if everything that's strictly below A is below some element of the finite set. And this is actually a new notion. It's not, I mean, you can get a generalized Amat pair just by making some member of F already an Ahmad pair with A, right? That would always satisfy it. But that's not the only kinds of Ahmad pairs that exist. There are actually degrees A, B, and C such that A and the pair BC is an Ahmad pair, but neither A and B nor A and C are an Ahmad. So it's a new thing. So now we showed that taking this construction, direct construction of no symmetric Ahmad pair, and adding in an extra layer of non-uniformity, we were able to show that there are no degrees A, B, C1 and C2 such that A and B are an Ahmad pair and B forms an Ahmad pair with C1 and C2. So here note that when we take C1 equals to C2, we get exactly the statement, the answer to this problem. There are no Ahmad triples. When we take C1 equals C2 equals A, we get no symmetric Ahmad. So this is a theorem that answers the question and generalizes no symmetric Ahmad. Yes?
Do you mean, oh, sorry. In the first theorem here, do you mean to exclude the possibility that B join C is above A?
But no, I don't mean to include it. If B join C is above A, there could be things that are below B join C that are neither below B nor below C. So it doesn't.
True, but okay. Just seemed to easier.
Yeah.
Okay.
That would be X. Okay. All right. So then with that solved, we can go back to and look at larger cases. Okay. So for n equals 3, let's see, how much time have I got? Oh, thank you. Okay. Okay, so for n equals 3, we actually have a full analysis, and it's more complicated than the n equals 2 case. So, but the theorem is, given all the possible instances, pretty succinct. So you can see what it is here, and we'll go through it, possibly not as slowly as I anticipated, as I planned, but we do have an actual complete dividing line between the yes and no answers. And you can see here that we are only mentioning, well, 7 instances, but they do account for all cases. And this was checked by Stefan and Junle on a bus to Chicago airport on their way to Dachshul. So they actually went through all possible 2 to the 8 cases to check that they all fit into this. But okay, so here's what we have. So first the yes side, which one, where can we see extensions? Okay, so first of all, the first extension that was in the previous, so you'll have to trust me here that I copied them correctly. The first extension is just the density thing again. So if I have 0, 0, 1, 0, 2, 0, 1, 2, I'll take it some degree below 0. Well, I'm given all possible choices for where it will be. It's either going to be just below 0, or it's going to be bounded by 0 and 1, or it's going to be bounded by 0, 2, or it's going to be bounded by 3. So yes, I can always extend to make this instance true. The second one in the yes column was actually exactly the fact that there are no Ahmad triples. So, okay, so here's how this goes. Well, in fact, it's our generalized version of no Ahmad. Okay, so suppose that I've embedded A0, A1, and A2 as an anti-chain. I would like to show that I can always either find something strictly below 0, or something strictly below 1, or something bounded by 0 and 2. Okay, so first, we'll have 2 cases. Suppose that A0 and A1 are not an Ahmad pair. This means there's something that's below 0 that's not below 1. Well, we have both possible cases for it with respect to 2, either just below 0 or below 0 and 2. Okay, so in this case, we're good. If A0 and A1 are an Ahmad pair, Then this is where the previous theorem kicks in. Then we know that A1 can form even a generalized pair with A0 and A2. So there'll be something below A1 that's not below either A0 or A2. And there you have it. So the answer is yes in this case. And then the final case, if we just have the singletons, then we need some extra. We need to prove something extra here. So we need to expand the no symmetric Ahmad pair proof to show this no symmetric generalized Ahmad pair kind of situation. So we need to show that it's not possible to have degrees A0, A1, and A2 such that A0 forms everything below A0 is either below A1 or A2. Everything below A1 is either below A0 and A2 or A2, and everything below A2 is either below A0 or A2. And to do this, you actually can take the idea in the no symmetric Ahmad pair, the modular idea in the no symmetric Ahmad pair, and generalize it to this case. So I don't have enough time to go through this in great detail, but let me just give you the highlights here. Okay, so given any set, we call a set G of A an A Goodrich set if it essentially has a similar structure to the theta of A that was used in the Goodrich operator theta applied to A, well, really to Ka, that was used in her proof of the no symmetric Ahmad pair. So we say that G of A is an A Goodrich set if there's a computable function F. This was the part where zero jump can figure out the limit, such that the limit for every n exists. If X is less than NF, it's in the nth column of G of A. If X is bigger than NF, it's not in the column. And then NF is going to be in, yes, NF is going to be in the nth column. It's going to code whether or not NF is in Ka. Well, Ka here is this uniform join of things reducible to. So this is extracting the properties that were used from the Goodrich operator. So notice that the way that we've set things up, G of A is always enumeration reducible to A because Ka is equivalent to A. Furthermore, if G of A is CE, then Ka is delta 2, which then means A is low. This is not important at all, but I think it's nice to point out as a property. And then Goodrich theorem can be now rephrased as saying that for every non-C set A, there's a Goodrich set G of A strictly below it. Now, Goodrich sets have nice properties. So there's a reason why we generalized this, extracted this as a separate notion, that they're kind of modular. If G of A is an A Goodrich set and G of A is bounded by B, some other set B, then if you take a B Goodrich set, you can find some other A Goodrich set strictly below it. So this is a really nice kind of relationship between Goodrich sets that allows us to prove things about it. And then this next theorem is the generalization of the theorem that said, if I bound the Goodrich set, then I can do the density construction to build a set that is strictly below me, but not below any of the sets whose Goodrich sets I bound. And you can even lift up this set that we're building above anything strictly below our given set A. So using these theorems together, I won't tell you how exactly, but you can kind of do it step by step to show that this generalization of no symmetric Ahmad. But I think these Goodrich sets are cool to look at and study independently. So someday in a future problem. In any case, so this proves the last step in the yes column. For the no column, well, the first case, the easy one, where the easy case where we have no singletons, that can be defeated very easily just by making everything pairwise a minimal pair. So that we saw already. And then for the other 4 cases, we need to do a combination of Ahmad pairs with minimal pair. In the first 2 cases, so in 2 and 3, this is fairly easy and done well. In the second case, we have direct construction. In the third case, well, you can do it either way. You can do a direct construction, or you can use Ahmad's nice modular proof of the existence of Ahmad pairs to combine it with minimal pair to get the result you want. The last case is the one that corresponds to the start theorem here, is the following. So to defeat 0, 0, 1, 0, 2, 1, 2, so 1 singleton and no triple, then what you would need to do is embed the partial order so that A0 forms an Ahmad pair with both A1 and A2, but A1 and A2 form an exact pair above A0. Okay, so that's the new theorem that needed to be proved here. At first, I had high hopes that you can use this modular thing, right? You have an exact pair. You need an exact pair for ideal of low degrees, which has a nice sigma 2 uniform presentation. Well, it turns out that building exact pairs, even for ideals of low degrees, doesn't always work. For example, if you think in the C degrees, the K trivials are an ideal of low degrees. The C K trivials are such an ideal, but they don't have an exact pair. So here we actually had to do a direct construction, and we believe that it works, but we haven't quite written out all details. Okay, so this is the case n equals 3. And then we fiddled around with n equals 4. Yes, I'm getting to the end. So for n equals 4, we thought about it for a little bit. And that led us to a conjecture for the general case for n greater than 1. And it is the following. So if you are given a family of non-empty subsets of now 0 through n, then let's call S0 all. So now you're looking at an instance where you have an, I guess, n plus 1 antichain. You're given some instance of our problem, and you can separate all the singletons in the instance in the set S0, and S1 will be all the others, all the elements from the antichain that don't appear as singletons in our instance. Then S is blockable if and only if, well, S0 is the empty set, right? If we don't have singletons, just the minimal pair, pairwise minimal pair thing will work here. Or if S0 is non-empty, then there should be an assignment. This is a function that takes elements from S0 to elements to possibly finally many elements in S1. And it satisfies some properties here. So the first property will allow us to defeat all possible singletons, because the idea is we're going to make any element in S0 an Ahmad pair with every element in its assigned set. And we need this to not be an element of our instance. This will defeat the singletons. And then everywhere else we'll do minimal pairs to, roughly speaking, to block all the others. So I had an example here for one particular blockable set to show you that it does satisfy this conjecture, but I don't think we have time for that right now. as Russell said, going to be recorded. Everybody wants to go back and check it. It is there. But we do have one side of this conjecture. So the only if direction of our conjecture is true. And that relies on now a further generalization of the Noah triple result. So the ultimate generalization of Noah triple is what we call it playfully, not in the paper probably, but this is what it is. So there are no degrees A, and now for A, we have finally many choices, BI, and for each BI, we have finally many choices, CIJ, so that, well, A is below none of the BIs, and each BI is below none of the CIJs that are associated with it, and A is a generalized Amat pair with the BIs, and the BIs are generalized Amat pair with the CIJ. So you can do that, right? Well, in the case where you only have one BI and you only have one or two CIJs, you get the previous Noah triple result, so this extent. And this theorem we have a proof of. So it proves one direction. For the other direction, we have to work on it. It looks like it's going to be a very big construction, putting all the different possible minimal pair and Amat pair constructions into one. It'll be hard to organize, but we're hopeful. So from here on, what comes next? Well, I suppose the next step is to allow one-point extensions to move freely around up or down. But for that, we would need to know if there are Amat pairs that join up to zero jump. And Lemp and Ung are actively working on this proof right now. It is an old project that originally started also with Iskander and Mars and got stalled because, well, people got busy with other things, I suppose. But the proof here seems to be really complicated. And I'm actually intimidated by the fact that we need to combine it with our already complicated things. It has injury along the true path and all kinds of nasty things like that. And yeah, so thanks for the attention.
Thank you very much, Mariya. Maybe one quick question before we change the talks over. We could give priority to the online people, maybe. Anybody online want to ask a question? Well, okay, thank you very much, Mariya.